human activities to the observed warming globally. That's what it means, because with science you can be able to quantify what are the contributions, considering at different forces, from natural, human activities, and so on and so forth. Even the greenhouse gases alone you can be able to give and see their contribution to the warming world that we are living in. So, next slide. This is the highlights of the global state of climate for last year, 2024. That spatial map is just the spatial average temperature globally. It is clear that the temperature in that single year, 2024, has increased more than 1.5 degrees Celsius. That is the annual temperature. I remember in the morning, Barbara talked about why we need to quantify the change. It matters a lot because we need to know. When you know the change, there are changes relative to something that happened. So that's why with the change, we will be able to monitor to know how much are we warming or what or not. So just a single message there, though the 2024 year, I can say it breaks the 5-second goal because we wanted to leave 1.5. But what does that mean? That one shows that, of course, in case that the road can go for 5 seconds are not out of reach. When we are talking about those goals, there's some, of course, clear measurement we use so that at one particular period we say we have broken the record for 1.5. So the message here is just to wake up us. It's just a wake-up call to ask all of us to know that we are putting ourselves, we are increasing the risk for our lives, economies, and our planet, of course. So because it is clear that the temperature keeps rising and we know what are the main contributions, those are anthropogenic activities. So the other table map, that is just reflecting the temperature over about 1. So you can see that in the recent past years, the temperatures are rising. So the mean, the surface temperature, the minimum temperature, even the maximum temperature. What is more interesting there is to see that the minimum temperature, when we talk about minimum temperature, we mean that the lowest temperature has been recorded on that particular day or in that particular hour. You can see that most of these minimum temperature for us, we record them during night time. So in other words, it means the night temperature are being warm, in a simple word. So let's continue. Next slide, please. That was also in the morning, it's all about the IPCC report. My key message there is for the second one, for the rainfall, the precipitation. We talked about the lack of data or lack of publication, especially in our region. So it is a call for all of us to act, because if we say there is no data, we need to do something for data to be available. Either there is no publication, so all of us behind this one here. So try our best and do research and even publish. Sometimes we do research, but we keep them in, let's say, in our cupboard, or we just put them in single website that is not even being visited by many scientists. So we need to do more of research. I don't know what is happening there. Go back. I'm done now. So, yes, that one.
Hello. Yes, it's better now. So I was saying, it's all of us to do something so that at least it will be well represented globally. So now coming back to the main aim of this presentation, for us to be able to even think about having high resolution climate models, or downscaling global climate models to have high resolution projections over Rwanda. It is one of the reasons why some of the research don't, even the findings, some of the reason we don't do research, some researchers, they say we don't have high resolution climate projection. Is that a reason? Probably yes or no. So, but when you looking at the global climate models, most of them, they have coarse resolution. You find a single model, it is all about 200 kilometers square, or 100, 50, 25. So you find when you want to do the analysis, let's say, for example, at country level, as Bamba was saying, and you find one model, just one resolution, it is even bigger than the size of the country. And you end up saying that Rwanda is represented by just a single value in that model. So we need high resolution climate model. That's how we came up with the idea of trying our best to see how we can downscale the global climate models. We put it at the higher resolution so that at least researchers, those who are making some more planning, designers, those who are dealing with infrastructure, those who are dealing with catchment, they will be able to have at least data about the projection in the area where they want to implement their project. That's why we initiated this, next slide, this project. So this project, I'm going to now explain how we came up with those high resolution climate projections over Rwanda. So those who are familiar with the model or modeling, we first look at the historical perspective of the model. So in this particular project, we did not run our own simulation because we had to, you know, it is computational demanding and it is a lot of physics behind it. So what we did, we used existing models. We used the CMIP6 models, global climate models. We picked up 9 models from coupled model intercomparison project phase 6. And those models, I'm sure here in the room there are those who knows the ISMIP, intersectoral impact model, intersectoral impact model intercomparison project. That is another initiative from PIC. They took those GCMs from CMIP6. They downscaled them at 50 kilometer resolution using the trend preserving quantile mapping method. So those ones, they are the ones that we picked and tried to do further downscaling using the same method, but now the observation we use, when we are downscaling, we use our own observation, the INAX dataset and the other dataset called CHERSA. The INAX is high resolution historical data we have at Meteo Rwanda. For rainfall, we produced them at 4 kilometer resolution. It is a combination of ground observation and rainfall estimate, the satellite one. And for temperature, we used the analysis and we blended them with the ground observation we have. The ones we record, when we talk about ground, they are the ones we record at station level. Those are point data. So we did the same method and we downscaled 9 models at 1 kilometer resolution over our country. So what we did, of course, after downscaling them, we tried to at least produce some results that can inform the agricultural practitioners. So we derived some indices, the mean temperature, the extreme temperature. When we talk about extreme temperature, sometimes some people, they just say it is extreme, but we need to know the intensity, the duration, yeah, kind of, even the frequency. So for here in this presentation, I will be talking about the intensity of extreme temperature. We counted them for 5 consecutive days. We also looked at the precipitation, the extreme precipitation, and also dry, what we call consecutive dry days or wet days. Let's continue to see what are the findings. Yes, as I mentioned earlier, before you use any model, even if you are done with downscaling them, at least you need to verify how do they replicate or represent your observation. There is spatial map for annual precipitation. The left one, go back. Yes, this one. Please don't move when I will be just telling you go to the next one. So the first one, like this one, this is the observation, the situation in Rwanda using the ground observation. The one I mentioned that was at 4 kilometer resolution. It is clear that in the southwestern part of the country, that is where we have high amount of rainfall. That is the annual one, the total sum for precipitation every year. That is the long-term mean from 1985 to 2014. That is the one we consider as the baseline or reference period in this graph. So the next one, it is the Chelsea, another data set from the Peak Institute. Actually, by the way, that data set is even available globally. So if you want to do the analysis using it, you can just go ahead and download it, even try to compare it with the other observation you have in your interest in the area you want to do the research in. It is also has high resolution, and as you can see, at least it has some similarity with our own observation, especially in the eastern part of the country, except that part of west and northwest, where you can see they underestimate our observation. We did the same for temperature, the annual temperature. You can see at least it is better representing our observation and also the Chelsea one. Go to the next. So those are now projected changes, the results we got from those high resolution climate projections. As you can see, actually this is the historical one, the historical for the year 2000. That is choosing 2000 or 2030, 2055, 2080. We were choosing the center year, because this is the projection. Let's say, for example, 2030, it is centered. 2030 is for the mean for the 2015 up to 2044. So the same for 2000 for historical, 2055 and 2080. And these projections, actually, what I forgot to mention here, we produced under different scenarios. So you know, when you are talking about the projection, we are dealing with scenarios. We have the ambitious scenario, the low, we have the middle one, and the business as usual. So here we have the three. For SSP 126, SSP 3.7, and also SSP 5.8. So those are simulations we have. You can see from the first column for that map for different scenarios. And by 2030, actually, it is interesting to see, like, in all emission, even if you try to change a bit the scale, for those change in mean temperature, you can see some difference. But there, you can see the difference is not that much. So, but as you go higher, by 2055 and 2080, of course, the difference is clear. And for, of course, even the most ambitious scenario, you can see the temperature will increase compared to what we experienced in the past. This thing that looks like Excel, these are the changes, actually, the quantified one. So, of course, that is spatial. If you go to each location, you can have its own changes. That is the good thing of having high resolution. But the statistics presented there, they are just for the country, the countrywide. Those are projected changes by 2030, 2055, and 2080. What is interesting there, when we quantify change, we need to test them. Are they significant? Those who are familiar with statistics, there are some testing methods we can use to test if the changes are significant or not. But for all scenario, for the temperature, it is clear that all changes are significant, and they are increasing. The other one, the temporal one, I think most of us, we are familiar with it. Those are emissions, and we try to see the confidence interval of them. So let's go to the next one. So these are now changes in extreme temperature, and they are counted for 5 consecutive days, and the threshold they considered here, it is temperature that is above 30 degrees Celsius. If we record that temperature for 5 consecutive days, that's how we come up with that intensity. Actually, the trend is almost the same like what we have seen for mean temperature, and except that for yes, they are all significant, by the way. They are all significant, and it follows the same trend as mean temperature. And by 2080, the hottest 5 days period per year could reach average value nearly 35.4. Actually, that one, the temperature of 35.4, in Rwanda, it was recorded once, if I recall very well from our observation, and it was observed at Kigali International Airport, just a single day. I don't remember exact year, but it is a long time ago. It has never been recorded again in Rwanda. So you can imagine in that 20 year, we'll be having those consecutive as normal. So go to the next slide. Yes, for precipitation. For precipitation, we wanted to, this is the annual total precipitation, projected one. The hatches, it is a bit different from what we used to see. Normally we use hatches when we are talking about the significance of those changes. But in this case, it is different story, because those ones, they indicate where at least less than 6 models, they agree on the change. When we have less than 6 models that don't agree with the changes, that's where we put hatches. So you can see for the ambitious scenario, SSP 126, the models we considered 9, or I can say maybe almost most of them, they don't agree on the change. But when you go to higher emission scenarios, they all agree on the changes. And there is numbers here. I guess you are a bit far, but you can't see them clearly. These, they agree on the change by 45%. There are some percentage. So, but when you look at the statistics all over the country, these, the bold ones, the black ones, they indicate that the changes are significant across the country. And the results presented here, actually, they are the ensemble mean. Sorry, I forgot to mention that one, but it's just for the ensemble mean. And for the results are significant for the business as usual scenarios, the SSP 5.8. So I think that's what I can say. And you can see the changes are clear, because there is nowhere we do have that the changes are negative. At least we can say maybe the rainfall will decrease. But it is, you know, what is most important for the rainfall, it is not only about the amount, but how frequent will those extreme rainfall occur. So in this presentation, I did not put the graph on that, but it is good to quantify that one. It is still a draft. We are still working on it, and we believe that by when we are publishing these results, we will be having those findings. Go to the next. It is the same for that one is for the season. You know, for us, because we were interested in agriculture, we also want to quantify those changes on agricultural seasons. The September to December season, the March, April, May season, those that we are most interested in, but you can go ahead even look at the GGA and the others. You can see the change are not different from what we have seen on annual basis, and this is critical for agriculture, those who are involved in agriculture, because whatever you are planning to do in agriculture in the next years, if it is a crop, by having this information, you can try to adjust, even predict what will be the yield, or even draw. Actually, the main aim of this projection is to alert us on drawing some mitigation or adaptation measures. Go to the next. It is the same. This is for heavy rainfall. The heavy rainfall for the scenario SSP 37 and the most ambitious scenario, they are significant, all of them, by 2050 and 2080. And the number of heavy rainfall days is high, variable. This is normal for rainfall. You know, rainfall varies a lot. Even in the projection one, they will keep varying. But projected increase in heavy rainfall is significant for the, as I said, for the rate years 2055 and 2080. So go to the next one. Just like a key message, and it's just to show you that the increase in daily mean temperatures we have seen, they also keep increasing. Even if I didn't show the graph for the two main agricultural seasons, they also keep increasing those seasons, and large increase in annual daily maximum temperature, as we have seen it. So the same as you can read. But what I want to mention here to emphasize on is the importance of this projection, actually. You know, it is as we said in the morning session, it was quite interesting. Like if you are doing the planning in 2030, if we are talking about NDCs 3.0, if we are talking of other policy documents, we have some targets. We can ask ourselves, did we do the further analysis to try to see how just not considering the global reports, did we try to use the scientific evidence from the local scale? it's just a question for me and for you, because we need to know this information, and this information, it can be cascaded to different, the purpose of this information to agriculture is a bit different from energy, it's different from health sector. So we need to tailor this information. You have information, but what does it mean to your sector? That is what the message I want to convey to all of us. Data are there. They are there as 9 models with high resolution. They are worth to be analyzed. Who is going to analyze them? It is not just Rwanda. It is all of us, scientists who are here. It's an opportunity for us to sit and do further analysis and try to, as Bamba said in the morning, at least have something that we can say about Rwanda, not just being said by other externals from, we can do it and we have that capacity. So I thank you very much. That's what I wanted to share with you in this afternoon. Thank you.
Thank you very much, Vedas, for taking us through a nice presentation on high resolution climate models data for agriculture. So we have time for like 2 or 3 questions. Yes, yes.
Maybe I'm trying just like this. Yes. You hear me?
Because they have online people.
They have online people. Okay. Well, thanks first of all for the presentation. I'm not a modeler, but I know quite a bit. Can you maybe tell us once more whether this downscaling is statistical or dynamic, and can maybe explain the difference, just the basic difference between statistical and dynamic downscaling? And then maybe just the last question, whether this is actually related to Cordex, which I understand regional downscaling is under the Cordex. Is that correct? And the other one is, can you just tell a bit the non-statisticians and people who are less into math talk about the uncertainty intervals? I was very happy to see it on the table. Obviously, we always have to remind that the map is just the mean, I guess, is the average trend. But can you walk us a bit through the notion of these uncertainty intervals that are quite significant? And thanks for putting them all into the tables.
Thank you very much. We have another question here. So you want to answer first? Okay, please answer.
Thank you very much for asking that question. Actually, you are even a modeler. Not, as you said, you are not a modeler, but you are. The fact that you know that there is dynamical downscaling and statistical, I understand that you have at least some notion about the modeling. So what we did here, we did the statistical downscaling, but we tried to bring in the topography features of the country. That's what we did. So for the... Okay, yes. Thank you. The difference between statistical and dynamical downscaling, when we talk about dynamical downscaling, we try to bring in the physics behind. In meteorology, when we are doing the simple one, like the forecast, let's say for example from the forecast, we use dynamical models. When we talk about dynamical models, they are physical and mathematical models built in. We try to do the initialization of those models. We ingest the historical one, and then we try to see the physics. There is what we call parameterization in those physical models. Then we get what the future will look like using the previous condition or initial conditions. But for statistical one, it's just simple. They are mathematical what I can say, simply mathematical equations. We try to see the past one and estimate, for example, the far future will look like this. Statistical, I don't know how, maybe Bamba will support me on that, but it is purely mathematics or statistics, equations we use, and try to load in the historical one and project the future. Yeah.
He actually answered right, but we can just answer it very short. It's like statistical downscaling is these are very simple equations to actually downscale to go at high resolution using the observations we have. If you want to do dynamical downscaling, you have to run a full-scale regional climate model forced by the model you want, the global model you want to downscale at the lateral boundary. That's the difference, yeah. Statistical downscaling is very fast. Dynamical downscaling is very, very, very slow.
The other question is about codex.
So the range of uncertainty intervals, how do you get it?
Oh, okay.
How do you get that, and what does it mean?
Yes, thank you very much for the nice question, and I know Bamba will just compliment me on that, because you know it's good to ask that question, the uncertainty in models. You know, for us who are dealing with projections, models most of the time they are subject to uncertainty, definitely. Because they are projections, they are uncertainty, of course. So how would we get them here? What we try to do, as there is something I showed, the agreement between models. We went ahead to compute the percentage of agreement between the models we considered. I said we had 9 models, okay? So in those 9 models, we want to see how each other agree on the other. We have an ensemble and we have individual models. So we quantify the uncertainty of those ones. If we have all models, they agree 100%, like what I showed you in the on temperature. All models, they agreed on the change. You get it? So the uncertainty there.
Yeah, so you have different uncertainties in the model. So when different models have different sensitivities depending on the equation they use, the way they describe the equation, and the parameterization that are inside the models. So basically you force the model with the same forcing, it will give you different results. So that is the model uncertainty. Because we don't know how the future will be, we have scenario uncertainties. All right? And then, yeah, we have those type of uncertainty scenario, model uncertainty. And then for regional climate models, we have lateral boundary condition uncertainties and so on. So you have different sources of uncertainties, all right, in climate models. So basically, those sources of uncertainties will combine to give you a whole uncertainty, okay? So you can quantify the uncertainties many ways. But then what he shows is a range of value. So he shows a range of value, which is the minimum, the model that shows the minimum value and the model that shows the maximum value, okay? And then you have this bold line, which is the multimodal ensemble. So that's basically, but, and it's true because that is the range of possible value we have for the 9 models. Yeah, across the 9 models. And that's a good way of showing uncertainties. But then I have a follow-up question before I come to you. So the follow-up questions that just come to my mind is, it's good. So this is an excellent data set, okay? And it requires a huge amount of computing resources to do the downscaling at 1 kilometer, right? So don't feel disappointed if I ask the question, okay? So if you change the 9 models and take other 9 models, because in CMAP 6 we have 32 models that deliver daily data, okay? So that is the spectrum of CMAP 6. That is the state of the art of climate change, the 32 models. So you pick 9 models. I'm saying 6 because ISMIP was having 6 models before, okay? So now there are 9 models. So you pick 9 models. If you completely pick other 9 models, which are still valid, so what will you have? Will you have the same thing? Because even in the 9 models, you correct them, you downscale them, and you still have differences among them. So which means it's an excellent data set, but the 9 models are not actually sufficient to give you a robust data. So be careful with that, okay? So basically, why ISMIP downscaled 9 models? It means they did some, okay, I'm not talking as ISMIP because I'm not ISMIP, but I know the story behind. They actually downscale, they validate all the 32 models and they pick 9 best. We all do it, no worries. Because it is to force the agricultural models, okay? The crop models, all right? So that was the idea, forcing the crop models, because you cannot use 32 models to force crop models, okay? So then you will need a server that will look like a city to store all the data. And that is acceptable. And why? Is because the impact model have a greater uncertainty than the climate forcing models, okay? So then if you pick 9 models that you validate and then you think they are the best ones and then you force your impact model, it's still fine. It is acceptable, okay? But then is these 9 models provide the climate information you need? That is something else, yes. Okay? Yes. Yeah. Okay.
Yes.
Thank you. My question was already asked by Martin, and I got the answer. Thank you. Yeah, yeah.
So let me ask this one, and then you ask, and then we close, okay? So the other question is, like, you have Meteo Rwanda data. What is the resolution? 4 kilometers. And then you have Chelsea. The resolution is 1 kilometer. So do you think there's a big difference? Is it a big deal? So I'm saying this because Meteo Rwanda capture very well the extreme precipitation locations. But that's not the case for Chelsea.
Yeah, sure. That's why they underestimate.
Exactly. And then you use Chelsea, which is already biased, to bias correct and downscale. So you have put the bias in your model.
Not really. We actually, what we did, after seeing that the Chelsea, they underestimate our observation, we tried to go ahead and use our own gridded data set. Yeah, that's what
the best
we did.
way.
Yes,
so the
but
best way
still,
is to use Meteo Rwanda data.
Yes, but still, if you see even the projection one, the historical one, they are not able to capture where our observation. Still, they underestimate. Yeah. And when you are dealing with extreme, you understand what will be the implication.
Definitely, definitely. So I think using Meteo Rwanda data is the way to go. 4 kilometers is still fine because going from 4 to 1, you're not gaining much. Yeah, so you're just increasing the computing resources for nothing. Thank you.
Yeah, actually, question 1, you asked it about the corrections. I noticed that one. The second now was, if now we are going for using inactive data, right? And then still underestimate. Have you tried to quantify the impact of topography in downscaling? I asked, during downscale, you used topography, you have added topographic features. Have you now gone back and checked the impact that topography has brought to the data?
Thank you, Joseph, for the nice question about after applying the topography, what was the impact? Yes, we did it, but I did not present it here in this presentation because we tried to see the RAPS rate. I don't know if you understand what is the RAPS rate. how the temperature changes with the topography. So we quantified that one, and there was like somewhere in the part where it is called Great Congo Nile, where we have those high topography. Even if we applied it, it was a bit not, what can I say? It did not take into account that, because we know the observation for that particular area, but if we see how was the temperature after applying it, it did not replicate it the way you wanted, like the observation. Also, it has an impact. But in the lowland, it was very well. It was even nice after applying the downscaling using the topographical data. The temperature were in agreement with our observation and the one. Of course, the past one, historical, not the projection one. Thank you.
All right. So let's have a round of applause for Vedas. Great presentation. Oh, so you had a question, right? So I think he had enough. So you keep your question for the next one, okay? Thank you very much, Dr. Vedas. And I would like to call Atanas for his presentations.
Thank you very much. Good evening. My name is Atanaza Fashimana from Rwanda, a PhD student from AIMS Research and Innovation Center. Okay. Thank you very much. And one of my supervisors is Dr. Bamba. And I even have other supervisors that I am not listing here. And I am going to take you through complexity of climate variables, interdependence, and their effects to agricultural sector in Rwanda. Next. So to make a small background and introduce this topic, we've seen that Rwanda, like many other sub-Saharan countries, like more than 95% croplands are rain-fed. It means in sub-Saharan Africa, we are doing these rain-fed agricultural practices. And more than 70% of farmers relies on rain-fed agriculture in sub-Saharan region. They just rely on it for their income and sustenance. And precipitation is not a standalone variable in a climate system. As you may be aware of, if we say like the climate system is the interaction of many components, maybe atmosphere, land, ocean, so that the whole system is having many variables that are interdependent. And global warming is about rising temperature and the climate ecosystem, and is what we have been listening since the morning, right? The global warming. And I was asking myself here, like, does global warming affect rainfall variability in Rwanda? Like question. And what about regional precipitation forecast bias in the Greater Horn of Africa? So the reason why I was bringing the Greater Horn of Africa is that I know that Rwanda is inside the Greater Horn of Africa, particularly when they do the regional forecasting at ICPAC, this IGAD Climate Prediction and Application Center. And I was also asking which climate forcing is critical to the change of surface air temperature in Rwanda. And the last one was like, what about precipitation amount and tea production in Rwanda? So like this last question, I was having the data for it so as to analyze and see. This is actually, okay. Sorry. Okay. This is actually like the rainfall data from robust accretion models and satellite observations for this greater horn of Africa that I was talking about. And you see the shapes like the precipitation satellite observation for Africa. And the rest of the models are coming from C3S, which is the climate change service that has European and American models for simulating precipitation. And this right plot is just looking at the distribution of the rainfall from these models using the kernel density estimates. As you may be aware of, check, it is quite to be sure that the data of precipitation is not normally distributed from the models. Next. From the regional perspective, when you go to regional precipitation seasonal bias, like if we say, for instance, the global circulation model that we have, how good is it even if you take a reference to this satellite observation, for instance, if you take shapes. So I was quantifying the bias here using the mean absolute error and the root mean squared error to see like how can we rank these models in terms of quantifying the temporal bias. And as you can see, this CMCC from Italy is highly biased compared to the rest of the models like NSEP, Meteo France, or Dechawet and this DWD, or the UK Met Office, even this ECMWF. Next. So, if we do the regional modeling now, and we are aware that the multimodal ensemble is minimizing the bias and capturing the spatial information more reliably compared to individual models. So how I was trying to know, if I have like a pool of models from the C3S, how many clusters maybe we be having from them? And I was using, for instance, the K-means clustering to see the possible clusters I may be having, and the possible clusters that you could have was like 2 from the 6 models from there. Next. So then I go ahead and do that clustering to see that the participant in each cluster that we may be having using 3 distinct formulation of hierarchical clustering algorithms, which are the unsupervised machine learning algorithms for just forming clusters. And for instance, this one is single linkage, which use like you do the chaining. You are clustering from your space and just forming a cluster by grouping your item against the whole space, and it's called chaining. And of course, as you may be seeing, I have changed various metric distance function from Euclidean, Canberra, and Chebyshev. I was just wanted to see if there is consistency unless changing the distance function, but it varies with changing the distance function. And of course, there's 2 clusters. There is a big cluster, and the remaining 2, for instance, in Chebyshev and Euclidean distance, are just outliers in the blue colors. And this one, the color map, like, no, the color map, this heat map here is just measuring the correlation between the models themselves. Next. The next one is average linkage formulation also, and go to B, okay. The average linkage, and the average linkage is quite similar to having the same clusters with the single linkage. And of course, but changing the arrangement of the models where they are, depending on the fact that this is based on centroid mechanism, right? You are now measuring the distance of this unit against the centroid of the remaining space. Next. This is word method, and this is somehow very crucial in this clustering formulation, where we have to maximize the distance between groups and minimizing within groups. It means we are making sure that we create a huge discrimination between the groups, but minimizing the within groups variability. So using this method, we could see that we could have a bunch of one cluster with the Meteo France, CMCC, and CMWF and MO, while the remaining and blue tend to be outliers of this system. And of course, what I can tell you for this word formulation, it is only using the Euclidean distance. So if we want to compare the whole formulation, we may take Euclidean distance to know what we can compare being aligned at a single distance function. Next. So now the question was like the potential multimodal ensemble of global circulation model. So why do we have to do the multimodal ensemble of global circulation model if we want to do, for instance, seasonal forecasting or even weather prediction? Why can't we use like a single global circulation model and do the seasonal forecasting, or even like weather prediction? What's the problem? So I wanted here to quantify or just see, like highlighting the impact of doing the multimodal ensemble. So as you can see here, like the multimodal ensemble is lying somewhere between some models, like in the mean. It means if we do the multimodal ensemble from the different distinct individual global circulation model, we are sure that we can minimize the temporal and spatial bias in prediction that we are accountable of producing. And of course, like the one I am presenting here is this in red color in the board one here. With these models, when I take accountable of the 6 model and see the ensemble average one here is just in that board red color here. Next. This one is now the potential of multimodal ensemble, but if we simulate, but using the spatial resolution, that one was on temporal resolution in the last presentation, the page. So this one, I was trying to do the spatial correlation and see if you do the spatial correlation between observation and individual global circulation model, how is it? So if you do this uniformly, like the uniform average, you may find out that it may be the case that your multimodal ensemble may perform poorly compared to one of the models because, of course, you didn't account for the weighted average. One of them may be having high bias and the other one was having very small bias. then when you are attributing this symbol, you may find out that even that symbol is not reliable. Next. So that one was like the regional perspective of modeling. Now let's go to rainfall and tea production in Rwanda now. So this is the study, and I extracted these results from the paper that you have published last year, 2024, with one of my friend Joseph. So I was having the data from NAEB quantifying the tea production, and meteorological variables from Meteor Rwanda, such like precipitation, and what you can see, I was having the data from NAEB of the tea production from Kitabi, Gisovu, Nyabihu, and Murindi. And this is just the annotation to show you where there's tea factories are. And this one, Murindi is here in the northern province, and Nyabihu here in the western, here Gisovu in the western, and this one Kitabi in the northern province, particularly in Nyamagabe here. So, and this is like the short overview of the tons of tea production they have produced during the 4 consecutive years ranging from 2017 up to 2020. So our studies was about to say, so if there is the rainfall variability, what about the tea production and the varying precipitation across these regions? Next. So this one is like the rainfall seasonal variation and short time trends. Like if I have this is from 2017 up to 2020. That's why I call it short time trend, because 4 years is a very short time period. And that's why I'm talking about variability, not climatology or something. Now here we are in variability. So, as you can see here, any month of July, you may see the minimum values of precipitation in Rwanda. And as you may be aware of, some of us who are Rwandans, it's when we have our summertime. Our summertime starts from June, July, and ends in like August, June, July, August. And sometimes you say extending to September. Okay, maybe. But the peak minimum value is here, the very minimum in July. And sometimes you may see in August, and sometimes, yes, August or July, you see the minimum precipitation. And this is the trend in production in these tea factories. And you may be aware of in Kitabi, there was a diminishing trend, meaning that the tea production was decaying, while the other tea factories was increasing the tea production for these 4 consecutive years. Next. So, now, we wanted to see the response of tea production to the rainfall variability in Rwanda. So, we used the panel data models to do so. And we used the 3 various formulation of panel data models, such as the ordinary least square, random effect, and fixed effects. And for the key result, we found out it in the fixed effect, where we account for the variation of, we account for the time varying variable, and the cross-sectional variation of variables, where we find out the rainfall was statistically significant on the tea production we were having, but also considering the temperature and fertilizer and the land. This land is just the plot size, the size of the land we have our tea plantation. And we find out that only this rainfall variable was statistically significant. Next. So this is just showing you the amount of precipitation they have been receiving during this period. And of course, you could see that there is the corresponding of proportionality in the production and the rainfall increment. For instance, check. When you look at Nyabihu with 93, for instance, if is the millimeter of received rainfall, you may see that it was account for these tons of tea leaves. And the maximum precipitation was to be found here in Murindi, but even the production, the maximum production is to be found in Murindi as well. Oh, okay. Good. So, next. So, I was talking about the climate variable interdependence at the beginning, as saying that the climate system is not, if you take one variable, it's not isolated. Probably the variation and change depend on like the changing other parameters as well. And here I was just trying to see the cross correlation between temperature and rainfall during this period from that Meteor Rwanda data of temperature and precipitation. And as you can see, like the perturbation, if we increase the rainfall today for this season, we are sure that the next incoming season there will be the fall of temperature. What does it mean? It is interdependent relationship, like increasing temperature will have a negative impact on temperature. Like if we increase precipitation today, you may even see it. If we are in rain season, we have the minimum temperature. That's what it means, this plot. Next. So this is another study when I wanted to see the response of surface air temperature and 6 forcings. I wanted to know, so if the surface temperature is changing, what climate forcing is to be accountable for it? So, and I used some SMIP6 models, and unfortunately most of them were statistically insignificant. Only this model, I did a lot like 10 of different models, but I decided to present 3 of them because only one of them was statistically significant with the F statistic less than the significance level of the 5%. And if it was statistically significant, but telling us that only the greenhouse gas was the contributing factor to this changing surface temperature. So it means these anthropogenic aerosols, anthropogenic greenhouse gas, and this is the natural forcing to simulate the historical surface temperature of Rwanda. Next. So this is like anthropogenic greenhouse gas from the statistically significant forcing there, and as you may see, if you see this greenhouse gas which was statistically significant among these variables, it is relatively close to this historical surface air temperature to show you that it is the major contributing factor to the change in temperature in Rwanda. Next. These are the spatial map simply and the temporal resolution show the considered 24 years range from 1980 to 2025, where we do this simulation. And go to next. I may tell you what I can take as a take-home message from these 3 different studies. I may tell you that rainfall is the key variable to rainfall agriculture. Like I take Rwanda, even because we don't have a lot of agricultural mechanization, we have but not enough. And in sample averaging may be useful to minimizing bias in seasonal rainfall forecast and increasing rainfall amount favorably increased tea production in Rwanda. And observed surface air temperature is varying to anthropogenic greenhouse gases. And of course, surface temperature and rainfall are interdependent. Therefore, modeling national climate change and variabilities should also consider teleconnections. Like if you say you have the precipitation due to this global circulation model, whatever. So did you account for any teleconnection like ENSO? What about when you increase La Nina or El Nino? What is the impact on your prediction? How is it? Is it causing a deficit, an excedence? Okay, thank you very much for your kind attention. This is the end of my presentation.
Thank you very much, Atanas, for taking us through your interesting presentation. So, 2 questions, quick ones.
Thank you, Atanas, for an impressive presentation. Mine, I want clarity. For the data, you have used CHAPS as observations. If I'm CHAPS, yes. Is that one used as observations? No, it was satellite data, yes? Okay. Now, no, yes, I want to ask. Was it 5 kilometer or the one with 25? Then what was the resolution of the model? Now, for Rwanda, why did you choose CHAPS instead of choosing other available data in Rwanda?
Oh, okay. So you answer first? Yeah, I answer. So, in Rwanda, I didn't use CHAPS data, first of all. I used the observation from Meteor Rwanda when I was doing on this agricultural impact tea production. So CHAPS is used for regional case. When I wanted to see the Greater Horn of Africa, to see the bias in this global circulation model they use for seasonal precipitation forecasting from C3S. Yeah, I wanted to see how far is a single global circulation model from these shapes. Yeah.
Yeah, of course. We don't have any other questions this side, so we go here. We're running out of time, so we have to.
Thank you very much for your presentation. I noticed that you included remote sensing observation. And your remote sensing observations are based on satellite. I want to know what are the satellites that you included in your work and at what resolution?
Thank you very much for this terrace observation on the regional case of the Greater Horn of Africa. The resolution was 0.25 cross 0.25 degrees. It's almost like approximately 25 kilometers by 25 kilometers longitude latitude grading. Saturated. No.
He didn't use satellite data. He used the global climate models for forecasting. And then I say global weather models, and then global climate. That's what it is. So any other questions? So last question there. Joseph, so let's just keep your question until coffee break.
Yeah, thank you so much for your presentation. My question is just related to your methodology. I would like to know, when you are computing the RMSE and the MAE, yeah, did you computed it related to what? Related to, yeah, I would like to know what was your, your baseline. Like, okay, yeah.
Good question. That was the last one.
Thank you very much for your question. So the baseline, I was just calculating the root mean squared error by taking the shapes as the ground truth and a single global circulation model as an estimate of this value. Good.
Yes, the whole region.
Question. All right, thank you so much, Atanas. A round of applause for him. And I would like to call B3 presentation, which is Ellen.
Thank you very much. I would like first to thank the organizer of this event. It's a very interesting event. My name is Elina Yanasenjung. I'm a PhD student. I'm a PhD student in the University of Cape Coast in Ghana. I'm about to present on the analysis of I'm about to present on the analysis of potential flood occurrence under climate change related variables in the coastal area of Kilifi. Is a part of Kenya. The presentation has the following outline. There is an introduction, there's a materials and method, result, and some references. Next, climate change has been presenting a significant threat to both present and future generation according to the production, and the challenges are observing through the iterated impact and hazard like flood. Flood has been significantly increased in both intensity and coverage globally, and it's causing a significant threat to human life, livelihood, and their properties. Kenya, like other parts of the world, they're experiencing flood significantly, especially low-lying areas like Kilifi. And this area is facing the challenge of flooding from different sources. Because this area is a coastal area, they're experiencing flooding from a high tide. They are also experiencing flood from fluvial and from fluvial sources. And this area is a Kilifi County, is a coastal area. According to the coastal county record, there have been reports that from 2009 to 2022, they have been experiencing a high flood where they recorded more than 40,000 people. That was been. This area they recorded more than 40,000 experienced the flood from 29 to 2022. Hundreds of lives and millions of dollars are damaged. For instance, in 2018, one incident, the county recorded more than 500 families displaced and injuries, and there were a loss of life. Looking on the next, please. Looking at all those incidents and challenges the area is facing through floodings, there is a need to do a modeling that is predicting the future flood incident, so that the policymakers, they can put it in the consideration for a future preparation and flood adaptation strategies. But the area, looking on the research that has been done, there is no work that is covering the modeling of future flood prediction. So this work is about to cover this gap. Next, please. This is the study area. Is a part of Kilifi County, which is located on the coastal area of the Indian Ocean. It's bounded with Tana River in the north, Mombasa County and Kwale County in the south, and in the east there is Indian Ocean. The county is having around 1,453,707 people, and is approximately 298,472 households, and the area is having land mass around of 12,609 kilometers. This is according to the Kenya National Bureau of Statistics for the census of 2019. The area is characterized by different impacts of climate change, such as floodings, drought, and coastal erosion. Next. So this study, I can remind that is ongoing research, which is a part of my PhD thesis. So is referring to climatical and hydrological secondary data that gathered from different institutions. We get precipitation and temperature data from Kenya Meteorological Department. River discharge data was got from online global of data center at 30-minute interval. Sea level rise data obtained from permanent service of sea level, and flood frequency data was obtained from International Red Cross in Kenya and disaster risk management from 2 institutions. Next. The study is using time series model, ARIMA with no composition, no seasonal decomposition analysis to do the trend and a pattern of flood occurrences. Next. So Next, please. Looking on the result from this data, we first did a descriptive statistic. This descriptive statistics is not really a part of analysis, but it's very important because we need to know the characteristic of our data. You can see if there is errors, outliers, and so the main annual flood event show us like the data observation data was from 1990 to 2023. So the main annual flood event shows us like in a year they are experiencing around 197 flood events. And we're showing that the average rainfall is 802.26 millimeter. River discharge, so showing that the mean river discharge is 214.6 meter cube by second. Sorry, the last one, it was mean average sea level, that's not temperature, is a mistake. Yeah, it's supposed to be a mean average sea level, like increase in sea level as in a year. They have been recording 8.46 millimeters, not temperature. My apology. I did a matrix correlation to show the relationship of a flood event and these climate change variables. Though I wasn't able to put everything in this PPT, but there have been, the results show that there is a high significance in the flood occurrences within these variables. The results show that it's an increase of precipitation is like flood occurrence is having a high positive correlation with precipitation. And also the main annual river discharge is having a high positive correlation with flood occurrence. And sea level rise is having a 0.58, like, which is a positive correlation with flood. Though there is not the direct, but the result shows that the increase in the temperature also increase the frequency in the flood occurrence. Next, we also did the linear regression analysis. We have seen that the correlation is showing us how they are correlated to each other from the variables, but also we need to know at each unit of increasing of each variable, how is it going to contribute in increasing of flood occurrences. From the result of coefficient is showing us that increase of 1 unit of river discharge is going to increase to the frequency of flood at 0.028 to each unit of river discharge. The result shows that at each unit of increase of sea level change or sea level rise is going to increase 0.33 of flood occurrence. The same way to precipitation, though the constant variable doesn't necessarily have a significant meaning in this result, but it's there as a coefficient of regression analysis. Next. This was a trend of variation in the change of flood frequencies and these variables. As you can see that in which year where the there have been a dropping of these variables. A flood frequency was also dropping. And when there was increase in there was a variation, flood frequencies was also increasing. So this is showing that the occurrences of flood frequencies or flood occurrences, it will depend on the change in the climate change variation. So as from the finding, as you have seen that there is a strong correlation with flood frequencies with these variables. On temperature, there is a need of reducing a source of the contribution to the temperature. As precipitation, once we reduce the contribution to our temperature, there will be a normalization to precipitation. For the sea level rise, once there is a mitigation strategies to the temperature, it will directly reduce the increase in sea level rise, because the sea level rise is occurring due to the increase of temperature. So there is a need to reduce the temperature so that we can get the reduction of sea level change and increasing. And from the river discharge mostly occurring due to the increase in precipitation. Precipitation, they are mostly causing a high river discharge. If we increase temperature, it will reduce temperature. It will automatically reduce each and every variable up there. So this is a result from flood prediction using a ALIMA model, which is having a 1-1-1. So we use the observation data from 1990 to 2023 to predict the future expectation of flood events. This red line is showing the past observation. Blue line is showing us the prediction of future expectation of flood events, but there is also the interval of uncertainties, because it's the prediction. You can't be precise on the prediction. There must be uncertainties for our prediction to may reduce or to may increase. So looking at uncertainties is very important, because as policymakers and planner for future flood mitigation and adaptation, there is a need to consideration of those uncertainties. And most important of this research, or a takeaway of this research, what I can say is a part of a disaster risk reduction or flood risk reduction due to the preparation according to the future production data and result. So this is the end of my presentation. Thank you very much. Those are some references. Thank you.
Much, Eileen, because we're running out of time, so we will take the last presenter and then have questions at the end, okay, for her and for the last presenter. So may I have Damascene Hakizimana? Presentation before modeling of water loss and demand risk in Rwanda. Eastern Rwanda probably irrigation schemes. So if you have questions for Eileen, so wait for the end of his presentation.
Good afternoon. I hope all of you are doing well. My name is Jean Damascene Hakizimana. I am a PhD student by research in water resources engineering. And I did masters in philosophy in irrigation and engineering from University for Development Studies in Ghana. So I'm just going to present an ongoing abstract. I just want to show my title, the modeling water losses and demand risk in Rwanda Eastern Irrigation Scheme. So for next slide. Next, please. Okay. So for this presentation, I'm going to talk about the background and problem statement. I also research objective, research methodology, expected findings, and conclusion and recommendation. So next. So for this photo, you see that this is the rainfall distribution pattern. So in Eastern Province, you see that we have the problem of a line. So this is the reason why in Eastern Province, we have the less water. So this is semi-arid area. You see for these farmers, it's looking like there is no water in that place. So which means that there is a land shortage event because there are drought. So for the crop needs supplementary in water and full irrigation. Next. So for this second photo, you see how the farmers in Eastern Province are struggling with the water scarcity. So for this shows that the irrigation must for agriculture transformation. So making efficient water management is crucial for productivity. Next, please. So for these research objectives, when I'm talking about the water losses and water demand risk on agriculture productivity in Eastern Rwanda irrigation scheme, I'm just showing you that for this photo, you see the linkage here, which means that in Rwanda, we don't have the problem of water because the problem is the management of water. So for this research, I'm just going to look for the water losses and the water demand. The water losses through the evaporation, the water losses through the seepage losses. For you see this left photo, you see there's the seepage losses. And also there is water losses through the distribution partners. So from the morning, we started talking about the rainfall distribution, increasing of the temperature, but there is a needs research for the water losses and water demand because it is very crucial point when we are talking about water management, which is interconnected to the climatic change. Next, please. So this is my research methodology. I will employ the HECLAS model. This is Hydraulic Engineering Center and River Analysis model, which will be used during a data analysis. We're talking from the morning session, we're talking about how can we get the data, but which model which can reflect accurately to the water dynamics, which is very crucial for the climatic change. So I will use also geographical information system in combination with the remote sensing data. So for this graph, you will see that how I will collect data, because you see the data gatherings. There is the seepage modeling data, geomatic data, geotechnical data, and hydraulic data. And also we have the operational modeling data, geomatic data, measuring data, and structure information. So when we are talking about the losses, the most losses we have here is the losses through the seepage. So this is why we need the calibration. I will also use the measurement seepage, permeability coefficients. And also for this, also we will estimate operational losses by calibrating and validation for these data. So for data analysis, I will use data collection but I will focus for field experiment. And also I will gather information through the questionnaire. I will also use the remote sensing data, hydraulic data, and meteorological data for this research. So when we are looking for these research methodologies, we found that adequate of water distribution and delivery and flow simulation, operation scenarios, and delivery discharge. So finally, we're just going to look at the total water losses during irrigation scheme, how those irrigation schemes are performing. We see that here in Rwanda, our countries invest more in agriculture sector, especially in irrigation. But in Eastern Province, we have the problem of water shortage. So, but for the management of those water, it's a problem. This is the reason why the most of water demand and supply, the high percentage of water are lost through deeper percolation, through seepage, through the evaporation. So this is the reason why it's very crucial to measure the total water losses. Because when we are losing the water, we lose also the energy, we lose also the money, which has an effect to the farmers. Especially from the morning we are talking about the last consumers for this research is the farmers or communities. So when I'm talking for the water losses, it is very crucial. This research has an impact to the consumers. Next slide. So for the modeling data, I will also the WIP model. This model will be used for the water demand. I will use this model basically on the crop type, crop stage, and seasonal patterns. And also this model will help me to know the water resources allocation so that I can understand the available water supply, and also to meet the crop water requirement, because I'm just looking on crop water requirement. So this model also has the water demand from the sectors. We see that we have a different water consumers for domestic and industrial agriculture and ecosystem. Those parts need the more waters. So we are talking about these models as a WIP model, which will help us to model this water demand. So for these parts, we are seeing that there's operating rules and policies and economic models and catchment hydrologies. So these models, in the combination with hydraulic and the WIP models, it will help me to understand the water demand and also the water losses through irrigation system. Next, please. So this is our expected result. By using those models, I think that the farmers, the more they're reducing the water losses, the more they're getting the higher yield, you see? For this is an expected result. They will also the net return, improve the user efficiency, and also this model will help us to reduce the greenhouse gases emission by increasing resiliency, and also we have the more expected result after. Next step, please. So this is the conclusion and recommendation. You see, for those farmers or last consumers, they are still struggling with the water linkage or the water getting out without no use for the crops. So this is the reason why we need to promoting food security and economic stabilities, and also to improve efficient water resource utilization by reducing agriculture water use. So at the end of this research, I will provide the recommendation to the farmers and policymakers to improve agriculture resilience and productivities. This is an abstract ongoing because I'm PhD students, I'm still searching the way of data collection and data analysis. I hope at the end of this research, I will come up with the recommendation. Thank you very much.
Thank you very much, Damascene. It's promising work indeed. Thank you. So we have one question for him, one question for Elaine. Any burning question? Okay. Question for Elaine or for Damascene?
Okay. My question is, from your conclusion, you concluded that temperature, precipitation, sea level are highly linked to the flow. I would like to know if during your study you try to estimate the contribution of each variable to this to the flow.
You understand the question? That's great.
Yes, as I said, it's ongoing research, and I have shown the correlation of flood occurrences with each variables, and I've highlighted the unit that can cause the increasing or decreasing of flooding for each variables. So I don't know if I've answered your question. Yeah, I didn't quantify in terms of percentage, but it quantified in time of frequency.
So she actually did regression analysis, and with all those variables, right? Each of them have its own coefficient, and then he has the constant at the end. So that's exactly what he did. Yeah, so I think, yeah, maybe in addition to that, you can look at the percentage contribution of each variable. But then flood exposure is more than that. So this is another question for you. So which means this Kilifi is just exposed to flood, no countermeasures. Are there countermeasures like a countermeasures for flood in this region of Kilifi? They are. Okay. So probably, okay, so it's good that sea level and then river discharge and precipitation will impact the flood levels, but you can also look at the exposure of that region. Yeah.
Yeah, actually the topic is assessment of risk and household vulnerability to climate-related flood in the coastal area. So this pattern I presented is like one part of, like one objective in 5 objectives. So this one can't cover everything that is going to be about my PhD thesis. That's why I've also worked on the vulnerability assessment. At the end, I'm expecting to do the risk assessment.
Thank you very much. So do you have a question for who?
Thank you so much. My question is related to Eileen. Why do you choose ARIMA model? Is it based on ICAC information criteria? If is that, what is the value of that ICAC information criteria? Why do you choose ARIMA model? Thank you. ARIMA model 1-1.
Yeah, so I choose ARIMA model. I can say that because it was in my convenient in analysis more than the other models. ARIMA 111, that was the fitting variables to the model. I don't know if you are satisfied. Thank you.
Are you satisfied or you just want to go for coffee break? All right, so thank you very much. This is the end of the session. Thanks for the presenter and thanks for you people for attending these sessions. Now we're going for a coffee break and then convene in the plenary room, okay? Thank you very much.